Okay, so I want to start with a number. And it's a number that, frankly, it keeps me up at night.
Oh, boy.
800 million.
It's just a staggering figure.
That is the active user count that OpenAI is serving for ChatGPT and its API. 800 million.
Yeah.
Now, usually when we talk about systems at that scale, Twitter, Facebook, Google, we're talking about these hyper-complex distributed architectures.
Absolutely. You expect to hear about sharding, data sliced across thousands of nodes, the work.
Eventual consistency headaches,
Mm-hmm.
all of it. But I was reading this technical disclosure from OpenAI.
Uh-huh.
It's based on insights from their engineer, Bohan Zhang. And I had to, double-check I wasn't misreading it.
Because they aren't doing this standard playbook.
Not at all. They're doing something that, it sounds almost reckless if you don't dig in.
Yeah, it does.
They're running the entire workload, so everything you type into ChatGPT, every history save, every API call on a single primary PostgreSQL instance.
One node. For all of it.
Huh?
It completely defies that common wisdom.
Right. If you went to a system design interview and said, I'll run 800 million users on a monolith, they'd show you the door.
You fail that interview, for sure.
So the mission for this deep dive is to figure out why they did this, and more importantly, how in the world it hasn't just melted into a puddle.
Right. We need to unpack this whole hybrid strategy they've got.
Because it's not just about buying a bigger server. It feels like a radical rejection of complexity.
I think that's the core theme. It's about resisting what you might call scale panic.
Scale panic. I like that. Let's dig into that. Because there's always this pressure, right? A startup grows, and suddenly it's, we need microservices. We need NoSQL.
We need to re-architect everything right now. Yeah, it's a common story.
So why did OpenAI resist that?
Well, just think about the actual cost of sharding. On paper, it looks great, infinite scaling. But in practice,
It's a nightmare.
it's a total nightmare. Your application logic suddenly has to know which shard the data lives on. You lose ACID transactions across different shards.
So if you need to join data, you're doing it in your application code, which is slow.
It's slow and it's buggy. You're basically trading infrastructure capacity for just a mountain of code complexity and operational overhead.
And OpenAI just said, no thanks.
Exactly. They said, let's see how far we can push a standard proven database if we just optimize the heck out of it.
So let's look at the actual setup. They call it an Azure PostgreSQL flexible server. Is this some kind of, magic hardware?
It's high-end for sure, but no, it's not magic. It's a managed service, but the architecture is classic. You've got that one primary writer.
Which is the bottleneck we're all worried about.
That's the one. And then they have nearly 50 read replicas.
50. Okay, so 50 copies of the data just for reading. That makes sense. If I'm just scrolling my chat history, I hit a replica.
Correct. And that handles a huge part of the load because AI applications are very read-heavy, but the write workload is still just massive.
And the numbers they shared are honestly impressive. Millions of queries per second.
With low double-digit millisecond P99 latency.
Okay, let's pause on P99 latency, because average latency gets thrown around a lot.
Yeah, and averages can lie. Averages hide the outliers.
Right. You could have a great average even if 5% of your users are, waiting 10 seconds for a response.
Exactly. P99 means 99% of your requests finish within that tiny window. It means the system is consistently fast for almost everyone.
And they're doing this with 5 nines availability, which is, 5 minutes of downtime a year?
Roughly, yeah. And keep in mind, the load on this one Postgres instance grew by more than 10 times in the last year alone.
The curve is just exponential, but the architecture hasn't changed.
Right.
Postgres is great, but it has known issues when you hammer it with writes.
Mm-hmm.
Specifically how it handles concurrency. You're talking about MVCC.
Yep. Multi-version concurrency control. This is usually the technical reason companies give up on Postgres at this scale.
So walk us through that. Why does MVCC become the villain here?
So MVCC is brilliant for data consistency. It means if I'm reading a row while you're updating it, I see the old version, you see the new one. No locks.
It doesn't overwrite the data.
It doesn't.
Yeah.
It marks the old row as dead and creates a brand new live row. This creates, it creates a lot of garbage. We call them dead tuples.
The database trash.
It's just database trash. And Postgres has this janitor process called vacuum that's supposed to clean it up.
But at OpenAI's scale.
The trash just piles up way faster than the janitor can clean.
And a bloated table means scans get slower and slower.
It kills your I/O. Your CPU is just spinning its wheels, sifting through all these dead rows to find the one piece of data it needs. It's the classic death spiral for Postgres at scale.
So they're basically sitting on this ticking time bomb of table bloat. And this is where that hybrid strategy comes in.
Right. They realized they couldn't just keep throwing everything into the database. They had to get strict.
Okay, let's go through these rules because this feels like where engineering culture really hits reality. Rule number 1, no new tables in the main database.
It's such a hard line. Imagine you're a product engineer, you've got a deadline, you just want to create a table for your new feature.
And the platform team just says, nope, the in is full.
Can't do it. I mean, it must cause friction, but it forces a completely different mindset. It explicitly stops the monolith from growing.
It caps the complexity right there.
Yeah.
So if I can't put my data in Postgres, where does it go?
That's rule 2. New workloads default to something else, like Azure Cosmos DB.
And why Cosmos? Why not just another Postgres instance?
Well, Cosmos gives you that horizontal scale out of the box. It's built for it. So if you're building, say, a logging feature with massive writes but simple queries, a NoSQL store is actually a much better fit.
They're matching the workload to the right engine.
Exactly. So they're not anti-sharding. They're just anti-sharding the monolith.
Got it. And what about the existing stuff in Postgres? The tables causing all that MVCC bloat?
That's the eviction policy. They actively hunt for the tables with the highest write volume, and they migrate them out.
It's like weeding a garden. You're constantly pulling out the aggressive plants.
It's a process of constant triage. By moving those high write tables out, they give the Postgres vacuum a fighting chance to keep up with the core important data.
So that's the big picture strategy. But you don't get to 800 million users just by moving tables. You need some deep tactical optimizations.
And the one that stood out to me was connection pooling.
This is so critical. Most developers know they should use a connection pool, but the numbers here were just drastic. They cut connection time from 50 milliseconds down to 5.
And people forget how expensive a new Postgres connection is. It's not just a TCP handshake. You've got SSL negotiation, authentication. The server has to fork a new process. It's heavy.
And if you're doing that 50 millisecond dance for every single API request,
your CPU is just saturated, shaking hands. You're not even running queries yet. By using a proxy, they keep those connections warm and ready. The app just grabs an existing one.
a 10 times improvement is just massive.
Yeah.
At millions of queries per second, you're saving thousands of CPU cores.
It shifts the bottleneck from connecting to the database to actually executing the query, which is where you want it to be.
Okay, let's talk about the nightmare scenario, the thundering herd.
The classic cache stampede.
Yeah, for anyone who hasn't been woken up by this at 3 a.m., walk us through it. What happens?
Okay, so you've got some expensive piece of data in your cache, maybe a config object that takes 200 milliseconds to compute from the database.
Right.
At millisecond 0, that cache key expires. It's gone. A user request comes in, sees the miss, and it goes to the database to recompute it.
But while it's doing that,
Another request comes in a millisecond later. It also sees the miss. It also goes to the database. At OpenAI's scale, you could have 10,000 requests arrive in that tiny window.
and they all hammer the database with the exact same expensive query.
All at once. Your database CPU spikes to 100%, connections time out, the app starts retrying, which adds more load, and you're down.
A self-inflicted DDoS attack. So how do they stop this? They use something called cache locking.
It's a really clever and vital pattern. When that first request sees a cache miss, it doesn't just go to the database. It first puts a little lock in the cache system, a key that says, hey, I'm working on this.
So the second request comes in a millisecond later.
It sees the cache miss, but it also sees the lock, and it says, someone's already on it. I'll just wait a few milliseconds.
So instead of 10,000 queries hitting your Postgres primary,
You have one. Exactly one. That query finishes, it repopulates the cache, the lock is released, and all those waiting requests get served instantly from memory.
it's the difference between a tiny latency blip and a full-blown site outage.
At this scale, it's absolutely mandatory. You just can't operate without it.
There's another layer here I thought was really smart. They use traffic lanes to isolate workloads.
Yeah, this is all about managing your blast radius. They route traffic to different database instances, or at least different pools, based on importance.
So the core ChatGPT experience gets the VIP lane.
It gets the VIP lane. And maybe that new experimental drafts feature gets the slow lane. So if some unoptimized code for that feature starts hammering the database, it might slow itself down.
But it won't take down the main service.
Exactly. It prevents a new feature from syncing the flagship, which leads us perfectly to the enemy of optimization, the ORM,
The object relational mapper, the
Yeah.
developer's best friend.
and the DBA's worst nightmare.
We have to tell the story. The 12 table join.
It's a true horror story. So for anyone listening, an ORM lets you write, say, Python code instead of SQL. You write user.posts.comments, and it magically fetches the data.
It feels like magic.
Yeah.
But that abstraction hides the cost.
A huge cost. So they found one query generated by an ORM that was joining 12 different tables.
12. How does the developer even write that by accident?
They probably didn't. They probably just traversed a relationship chain in the code. Object.parent.child.owner.settings, And the ORM just tried to be helpful and do it all in one go.
And when you ask Postgres to join 12 tables across millions of rows, what happens?
The query planner it explodes. It takes a ton of memory. It locks rows. And during traffic spikes, this one query caused multiple high-severity incidents.
It's the butterfly effect. One line of Python causes a hurricane in the database.
And the lesson is that at this scale, you cannot blindly trust generated code. You have to write the SQL by hand for your critical paths.
You have to actually look at the queries. It sounds so tedious.
It is tedious, but convenience is a risk factor. You trade that initial developer velocity for long-term system reliability.
Which brings us to the final piece of the puzzle. Their operational discipline. The rules they have for their humans are intense.
They are ruthless.
Take the timeout policy. A schema migration like adding a column. If it takes more than 5 seconds, the system kills it.
5 seconds is nothing. In a lot of companies, migrations run for hours over a weekend.
So why so strict?
Because a schema change needs a lock on the table. And if you hold that lock for just 10 seconds on their primary database, you might queue up 50,000 writes behind it. You create a backlog you can't recover from.
So if you can't do it in 5 seconds, you just can't do it.
You have to find another way. Break it up into smaller pieces, do it asynchronously, or just don't do it.
Then there's the data backfill policy. This one blew my mind. Running a script to update old data.
Update all users where X equals Y. Yeah, we've all done it.
At OpenAI, they rate limit those internal tools so aggressively that a backfill can take weeks to finish.
A week or more. And this is such a profound insight. We always worry about external traffic crashing the site. But how many outages are caused by an internal dev just running a script?
I'll just quickly fix this data, and boom, the site is down.
Exactly. They treat their own internal tools as untrusted and throttle them to make sure they never compete with user traffic for resources.
It's a policy of extreme patience.
Mm-hmm.
Stability over everything else.
It's the only way to be safe at that scale.
So, to bring it all together,
Mm-hmm.
we have a single Postgres node handling writes for one of the biggest apps in history.
And they manage it by being ruthless. Offloading new data, caching intelligently, reviewing every critical SQL query by hand, and enforcing insane operational timeouts.
It's a total triumph of optimization over just, re-architecting for the sake of it.
It really is. And it's so counterintuitive. We're always sold this idea that modern has to mean complex.
Yeah.
Kubernetes, microservices, service mesh.
And those things are useful. But complexity is a tax. You pay it every single day in debugging time and mental overhead.
And OpenAI is proving that boring technology can scale way further than most of us think.
But there has to be a limit, right? They're at 800 million. Can this get them to 2 billion?
That's the billion-dollar question. I mean, vertical scaling eventually hits a wall of physics. You run out of cores, you run out of memory bandwidth.
So eventually they might have to shard that core database.
Eventually, probably. But think about how much time they've bought themselves. They've delayed that incredibly complex migration for years, letting them focus on what matters, building better AI models.
That's the key right there. Complexity delayed is value earned.
Well put.
So here's the thought I want to leave everyone with. You are probably not building ChatGPT. You almost certainly don't have 800 million users.
Statistically speaking, no.
So if OpenAI, powering the most futuristic tech on the planet, can get by with a boring, standard, single-node database, what complexities are you adding to your work that you don't really need?
Are you reaching for sharding or microservices just because it feels like what you're supposed to do?
Or is it because you haven't taken the time to truly optimize what you already have? Maybe proven is better than shiny.
I'd bet my database on it.
Thanks for diving in with us. We'll see you next time.